So let's now look at our fourth and final transfer path, which is electromagnetic fields, or radiation EMI. And so here our transfer path is resulting from radiated electromagnetic waves, and so we can connect this to what we've talked about before in our high frequency unit, where we said we want to keep our circuit size smaller than about 5% of our wavelength, 5% of lambda. And we wanted to do that to avoid having any electromagnetic or EM radiation. And so of course our lambda is going to be related to our frequency of operation. And if our circuit is too big, then we're potentially emitting this electromagnetic radiation, which is losing energy and also potentially interfering with other circuits. So one thing to note about this electromagnetic fields, or this radiation EMI, is that it's not going to be as localized as our capacitive or inductive EMI. So not as localized as our capacitive and inductive EMI. And so that's what we looked at in our previous two videos when we considered our electric field and our magnetic field respectively. So let's talk a little more about our behavior of fields for a second. So our behavior of fields we can understand it a little better if we look at this ratio of a distance to our wavelength. So let's take a ratio of distance normalized to wavelength. And so what that's going to do is that's going to allow us to sort of compare over different wavelengths or different frequencies, in other words. And so that ratio is going to be 2 pi r divided by wavelength lambda, where r is just going to be the distance from the source. And so what we can say is if this ratio, this normalized ratio of 2 pi r over lambda is less than unity, then we're in a region called the near field. And so we can see the distance that correlates to the near field is going to change depending on our frequency of operation, because of course as our frequency changes, our wavelength is going to be changing as well. So this near field is sort of an important term to understand as we work in electromagnetics. And it turns out that in the near field is where we have most of our capacitive and inductive EMI taking place. So most of our capacitive and our inductive electromagnetic interference is here in the near field. So sort of coming at this from another direction, we can say the magnitudes of our electric and magnetic fields fall off at known rates. So magnitudes of our electric and our magnetic fields fall off at rates of 1 over r squared or 1 over r cubed. And so by fall off, I mean they're decreasing by 1 over r squared, where again r is a distance from the source. So we can see it's dropping pretty drastically as we move away from the source. And so we could put that in terms of the power of these fields. So our power then is going to fall off at 1 over r to the 4th, or 1 over r to the 6th, because our power is going to be related to our magnitude squared. So squaring our terms above, we get an even sharper drop off for our power. So this is for our magnetic, so our electric and magnetic fields. But if we look at the magnitudes for our radiated fields, they fall off a lot more slowly. So magnitudes for our radiated fields are going to fall off at a rate of 1 over r. And again, you're just kind of having to take my word for this at the moment. We'll get into this a little bit more in a later class in electromagnetics. So they're falling off at a rate of 1 over r, which means our power density, is going to be dropping at a rate of 1 over r squared. So power density falls off at a rate of 1 over r squared. And so we can see, of course, that's a lot slower decrease compared to 1 over r to the 4th or 1 over r to the 6th. And so a common name for this sort of relationship is our inverse square law. And so we're not going to deal with that too much, but that's just one of those things that I want you guys to at least have seen and be somewhat familiar with. Okay, so let's look at the simplest type of radiated electromagnetic wave, which is something called our transverse electromagnetic plane wave, or TEM wave. And so you kind of have to use your imagination a little bit here because it's a little difficult for me to draw well in 3 dimensions, but what we can see is basically we have an electric wave which is in blue here, and we have a magnetic wave which is in red. So here we have our magnetic wave H. And so let me draw this sort of as a cross section in 2 dimensions so we can see this a little better. And so I should mention too, this is a radiated wave, so it's moving through space, and our direction of propagation is going to be in this z direction. So direction of propagation. And so what we notice is that, and it's going to be more clear in this next figure, but our electric field is along our x-axis, our magnetic field is along our y-axis, and our direction of propagation is along our z-axis. So for instance, if I come in here and draw this in 2 dimensions with our x and our y, what we would see is that we have our magnetic field along our y-axis, so that would be our h, which is equal to some magnitude h naught times cosine omega t in our y direction. And then we would also have our electric field, which is in our x direction. So this would be our electric field, which is equal to some magnitude E naught times cosine omega t, and that's in our x direction. So those are just unit vectors for our x and y direction, the u of x and u of y with the little hats. And so again, what we see is that our electric field and magnetic fields are perpendicular to one another, and both of them are perpendicular to the direction of our propagation. And so for this particular wave, we could say that it's polarized in the x direction. And so all that is just the direction or the orientation of our electric field. So in this case, it's along our x-axis, so we would say this TEM wave is polarized in our x direction. Okay, so with all of that in mind, let's sort of come back to reality and look at sort of a practical example, just real briefly. So let's say we have some industrial setting, and in that industrial setting we have some radio frequency heater which is being used to heat bags in order to seal them. So this RF heater is in this factory, and so a typical frequency for this would be a frequency of 27.12 megahertz. And so again, we could relate this back to what we talked about in our high frequency unit. If we look at our frequency allocations, we could see that this falls into one of our ISM bands. And so remember, ISM was industrial, scientific, medical. So these are sort of really narrow bands at certain frequencies. And so what we could say is, with this frequency, we could calculate our free space wavelength to be equal to c over f, realizing that really the velocity might be a little bit lower than the speed of light. But if we use that sort of as an upper limit, we could say that this wavelength then is approximately 11.062 millimeters. Sorry, not millimeters, meters. So if we want a circuit with this RF heater to not be emitting electromagnetic radiation, remember we had said we want our circuit to be smaller than 5%. So we want our circuit to be smaller than 5% of our lambda. So in this case, that's going to be approximately half of a meter. So let's say somehow this RF heater gets coupled to an extension cord that's on the order of a few meters long. So let's say our RF heater is coupled to an extension cord that is several meters long. Well, so because that is larger than our rough sort of rule of 5% of lambda being 0.5 meters, we're going to have electromagnetic energy radiated from that circuit. And what's going to happen is that because this has a longer range than our electric and magnetic fields, so we're not limited to the near field, because remember, we don't have this sharp power fall off, we have this 1 over r squared fall off. So if there's enough energy in this RF heater to transmit far enough, we can see interference as far as meters away. So interference meters away from our source. And so again, this sort of contrasts with our electric and magnetic, which are going to be more localized. But in certain cases, if we do have a large enough energy, we can be seeing electromagnetic interference from relatively large distances.